Today, we're talking about giants, and I mean truly massive machines. The diesel engines that power the world's cargo ships are some of the biggest, most powerful engines on the entire planet. We're talking engines that are stories high, with pistons you could literally stand inside. But that brings up a really fascinating question. Right? You can't just hook it up to some machine you'd find at your local car garage. It takes this really clever multi-step process using some absolutely brilliant mechanical instruments. So let's dive in and see exactly how the engineers get it done. Okay, the first thing you have to understand is that an engine's power isn't just one single number. There are two. You've got the theoretical power, the raw energy created by that explosive combustion inside the cylinder. We call that indicated power. But then you've got the actual usable power that makes it all the way to the propeller after fighting against all kinds of friction, and that's the brake power. Our whole mission today is to figure out how to measure both. So, first up, we have to find a way to peek inside the fiery heart of the engine itself, right into the cylinder where all that power is first born. And to do that, well, we're going to need a very special tool. This right here is the engine indicator. I want you to think of it like a mechanical artist. Its whole job is to reach inside that cylinder and literally draw a picture of the invisible, incredibly violent pressure changes that happen during a single power stroke. It's an amazing way of making the unseen seen. I mean, isn't this just incredible? The mechanics are so beautifully simple. You have to remember, before we had all this advanced electronic equipment, how could you possibly know what was going on inside that explosion? Well, this was the answer. A tiny piston feels that immense pressure, which pushes a carefully calibrated spring, which moves a little stylus up and down. At the same time, a drum covered in paper, which is physically linked to the engine's main piston, moves back and forth. What you get is a perfect physical map of pressure versus volume. And here it is, the final product. This loop, this kind of strange-looking shape, is what's known as a pressure-volume diagram. And it's not just some random squiggle. The actual physical area inside that line represents the total amount of work done by the gases on the piston during one cycle. So the bigger the area, the more work and the more power. Which, of course, brings us to our next big engineering challenge. We have this beautiful drawing of the engine's work, but it's a totally irregular shape. You can't just use a simple formula like length times width. So how in the world do you turn this drawing into a hard number? For that, you guessed it, we need another incredibly clever mechanical device. It's a tool that was designed specifically for this exact problem, and it's almost like magic in how simple it is. So say hello to the polar planimeter. This thing is basically an analog computer from a time way before digital calculators. It was designed for one specific beautiful purpose, to precisely measure the area of any two-dimensional shape you can trace with it. An engineer would just carefully trace the stylus of the planimeter all the way around the outside of that pressure volume diagram. And as they do it, that little wheel on the device, it rotates and it slides, and a super precise dial gives a numerical reading of the area. It's just pure mechanical genius, turning a physical shape into a real quantitative value. So why do we need that area number so badly? Well, it's all about finding this absolutely crucial value, the mean effective pressure, or MEP. By taking the area we just measured and dividing it by the length of the diagram, we can figure out the average effective pressure that was pushing down on that piston during its power stroke. It's a way of taking that whole complex pressure curve and just simplifying it into a single, really useful average. And that MEP value, well, that is the golden ticket. Once you have it, you can plug it into a formula with the engine's dimensions and its speed to calculate the total theoretical power being produced inside those cylinders. We have now officially measured the indicated power. But remember, that's only half the story. Okay, so now we have to leave the inside of the engine and head to the outside, to that massive output shaft, to find out how much of that power actually survives the journey to get there. See, the indicated power is the raw energy born from combustion. But on its way out, that energy has to move heavy pistons, turn a gigantic crankshaft, run pumps, all sorts of things. Friction and what we call these parasitic loads just eat away at the total power. And every little bit of that lost power is wasted fuel, which means wasted money and extra emissions. What's left over at the very end? That's the brake power. So how do we measure what's actually left? With this absolute beast, the dynamometer. You can think of it as a huge, programmable, water-cooled brake that gets hooked right up to the engine's shaft. Its job is to apply a very precise, measurable load to the engine. It's basically challenging it to an arm wrestling match so we can measure its real-world strength. So inside the dynamometer, the engine spins a rotor through a fluid. Now, this tries to drag the outer casing, the stator, along for the ride. But that stator is held in place by a very precisely weighted arm. The exact amount of force it takes to keep that stator from moving gives us a perfect measurement of the engine's twisting force, its torque. And once we have that torque value, the final step is actually pretty simple. We just combine that twisting force, the torque, with the rotational speed of the engine, its RPM, and with that, we can calculate the brake power. This is it. This is the real deal usable power that the engine actually delivers to do work. Okay, so we've done it. We have measured the power that was born inside the cylinder, and we've measured the power that actually gets delivered at the end. Now it's time to put them together and give this engine its final grade. So on one side, we've got the indicated power. That's the total theoretical output that we calculated from our pressure diagrams. And on the other side, we have the brake power, the actual delivered power measured by our dynamometer. You know, the difference between these two numbers, it tells us everything about the engine's internal health and ultimately its profitability. For a big marine diesel engine, a typical number you might see when you compare the two is right around 85%. But what does that percentage actually mean? It means that 85% of the power that was generated in the cylinders successfully made it all the way to the output shaft. That other 15%? It was lost to friction. This ratio, brake power divided by indicated power, is called mechanical efficiency. And for a marine engineer, this percentage is the engine's ultimate report card. In an industry where fuel is one of your biggest costs, even a tiny drop in this number can signal millions of dollars in losses, or catastrophic failure just over the horizon. So let's just quickly recap the 3 pillars of this whole process. It all started with the engine indicator, which drew that crucial pressure volume map for us. Then, the amazing polar planimeter translated that map into a number, which let us calculate the theoretical indicated power. And finally, the dynamometer measured the real-world torque to give us the actual usable brake power. And bringing all that together gives us that one key metric. Mechanical efficiency really is the whole story in a single number. It's the measure of how well this mountain of moving metal can turn a chemical explosion into the force that literally moves the world's goods across oceans. Which really leaves us with a final thought. You know, these century-old mechanical principles for measuring power are still fundamental today. They allow engineers to diagnose problems, to refine designs, and to push for every last fraction of a percentage point of performance. So the real question is, how close to a truly perfect, 100% efficient engine can this kind of precise measurement actually help us get?